Hello. In today's video on the kinetic theory of gases, we are going to continue with the degrees of freedom. Now, the degrees of freedom of a mechanical system, it can be defined as the number of possible independent ways in which the position and the configuration of the system may change. So, if we consider a particle moving along the x-axis of the coordinate system, then if it is moving along the x-axis of the coordinate system, then uh, at any given instant of time its position can be defined by a single coordinate, that is the x coordinate. So it's moving like this, and at any given instant of time we just need to put the value of x over there, so x coordinate defines its position over there. So the number of so this is, let me just write it, that it is particle moving along x-axis. So the particle moves along the x-axis and we just need one coordinate to express the position, and so here the number of degrees of freedom, or the degrees of freedom, just to write down. So that is equal to 1 over here. So n here is equal to 1. Similarly, if we are considering it to be moving on a plane, so that requires two coordinates to express it. So two coordinates are giving its position, and as a result of that, the degree of freedom over here is going to be 2. And same is the case with a bird flying maybe in space, in the three-dimensional space. In that case, the degree of freedom is 3. Now consider, so I'm just mentioning it over here as we are on a discussion over here. So for 3D space, we have the degree of freedom to be equal to 3. Now, in case we have a diatomic molecule, so for a diatomic molecule, we can express the, now this is supposedly a diatomic molecule, and they have a spacing which is fixed. Now, although we will be saying that we need 6 variables to give their positions, but there is one constraint that is present, which is the connection between them. They are not exactly connected by some material, but a diatomic molecule, they stay together, the atoms stay together, the two atoms which constitute or form the molecule, and as a result of that, the degree of freedom, there's no freedom available for them to move along that constraint line. The constraint, the line of constraint that is present between them, they cannot move, they are not eligible, or they are not allowed to move along that line. So as a result of this, the degrees of freedom in this case will be the 6 coordinates, which will be for the first atom and the second atom, but the constraint reduces that by a factor 1. So here the degree of freedom is simply 6 minus 1, which is equal to 5. So similarly, for a triatomic molecule, now this is a triatomic. Now in this case, we have the similar condition where we have 3 constraints, and there will be 3 times of 3, which is for the space, 3-dimensional space that we are considering the atoms or the molecules to be present in. That will have 9 coordinates to express the position of the 3 atoms that constitute this triatomic molecule. but again we have three constraints which restrict them. So the degrees of freedom in this case is 9, that is 3 times of 3 for 3 atoms constituting the molecule, minus the 3 constraints, and that results in 6. So in general, if we are considering an independent not connected particle, the in case we have n number of particles, so in case we have n number of we'll say not connected particles, n number of particles which are not connected. So in that case, what we are getting is the degree of freedom in that case is simply 3 times of n. But if k are the number of constraints, or k is the number of constraints, then the degree of freedom reduces to 3n minus k. This is the general case of the degrees of freedom or degree of freedom of a given system. Now the degree of freedom for a gas molecule can be given as follows. Now for a monoatomic gas, the molecule is considered to be a point mass under ideal condition that we already discussed, and it only possesses translatory motion. So there's no chance of it because we are considering the point mass, so there's no chance of it being rotated or executing any rotational motion about any axis that is passing through it, and due to its negligible size, of course. So as a result of that, the degree of freedom for this is simply given by n is equal to 3, not considering the rotational case, rotational motion. I'm giving a shorthand to rotational part. So not considering the rotational motion, we are obtaining this the number of degrees of freedom to be equal to 3. Obviously this is a point mass consideration. Now because of that, we also have the case of diatomic gases. So in case of diatomic gases, now as for the diatomic gas, the type of motion depends on the temperature, and at low temperature the gaseous molecule that only executes translatory motion, and as a result of that the degree of freedom in that case is 3. While in the medium temperature, that is from 250 to 750 Kelvin, in that range you have the translatory as well as the rotational, but in case of rotational we have only 2 components to be operational. We'll see how, and that sums up to the degree of freedom being equal to 5. Now as for the rotational case, what we see is let us consider these molecules over here. These are the diatomic molecules and they are somehow connected like this, and this center of mass which is existing between them, that coincides with the origin of some coordinate system maybe, and let's consider these diatomic molecules to be present along the x-axis. As a result of that, this being the x-axis, this is the supposedly the y-axis, and this in 3-dimensional case we are considering to be the z-axis. Now obviously they will be rotating about both those axes, that is for y and z, but in case of x, if they were to rotate about this axis, now this rotation won't really contribute to the moment of inertia about the x-axis, because the distance from the x-axis is going to be 0. So with the moment of inertia about that axis being equal to 0, that won't contribute to the energy terms, that is the rotational energy terms, and as a result of that, that degree of freedom won't really count. There won't be any exchange of energy due to the rotation about the x-axis, and as a result of that, that is not taken into account, and so we have the number or the degree of freedom in this case to be devoid of that due to the x-axis in the rotational case, and therefore we have it to be equal to 5. Now, considering the triatomic gas, now we also have to consider the high temperature case. So at high temperatures, that is, let's say above 750 Kelvin, that is, so at higher temperature, at high temperatures what we get is the that is beyond 750 Kelvin, we obtain or we get another additional motion that is associated with the diatomic gas, that is the vibratory motion. That is, along that x-axis, the atoms, they tend to vibrate, and as a result of sometimes coming closer to one another, and at other times going away, moving away from one another. So that's the kind of motion that they execute, and as a result of that, that adds to one further degree of motion, degree of freedom. And so the vibratory motion along with the translatory and rotational, we get vibratory motion or vibrational. And as a result of that, the degree of freedom in this case, marking it over here, the degree of freedom in this case is going to be 5 for those two, and for vibration we have 1, so this is 6. But for mostly for calculation purposes, we extend it to n is equal to 7 for calculation purposes. So that is encircled because it's a special condition that we are considering, that is only for calculations. Then next we have the law of equipartition of energy. Now, in any dynamical system which is in thermal equilibrium, this is the statement of course, the total energy is divided equally among all the degrees of freedom, and energy per molecule per degree of freedom is half times of kT, where K is obviously the Boltzmann constant and T the absolute temperature. Now, if we consider a monoatomic gas molecule, the molecule possesses only translatory motion as discussed earlier. Now, as the molecules they collide against each other, the number of collisions suffered by each molecule is of the order of 1 billion. It's very huge. And as a result of this large number of collisions per second, the three components of the velocity of the molecule become equal to each other. So we have Vx to be equal to Vy to be equal to Vz, which are the components of the velocity in along all the axes. And as a result of that, that also results in the kinetic energy values to be the same, that is half mvx squared is equal to half mvy squared plus half mvz squared. So this is, let's take it as E for now. So the kinetic energy per molecule per degree of freedom is this. Now the kinetic energy per molecule will simply be equal to the sum of all these, considering all the degrees of freedom. I've mistakenly written a plus over there. Let me correct. So this is as I mentioned, this is the kinetic energy per molecule per degree of freedom. Now, so the kinetic energy per molecule only will include all the 3 degrees of freedom, and that goes to 3e. Now, as a result of the kinetic theory of gases, we have the kinetic energy per molecule to be equal to 3 over 2 kT. If you remember, you can go through the playlist and check for yourself that we have obtained the expression for the kinetic energy per molecule to be 3 over 2 kT. And so if we compare both of these things that are there. So we have the energy to be equal to half times of kT, K being the, as I mentioned, is the Boltzmann constant over here, 1.38 times of 10 to the power 23. And this gives the kinetic energy per molecule per degree of freedom, with the degree of freedom that is 3 that has been divided. So we get this. Now if we wish to obtain the mean energy, so supposedly we wish to obtain the mean energy, usually represented by U. So if we are considering 1 mole of gas and it contains n molecules, so where n is obviously the Avogadro's number, so with n being the degree of freedom, we have the kinetic energy per molecule to be equal to n times of half kT, right? And the kinetic energy of 1 mole of the gas is what we call as the mean energy, which is to be obtained. And or it is also termed as the internal energy, which is why we are using the popular symbol U. So the internal energy of the gas is therefore equal to n times, that is the Avogadro's number, times of n over 2 kT, which is the kinetic energy per molecule, and that will give us n times of n over 2, but k here is r over n, that is the Avogadro's number over there multiplied with the absolute temperature. So the capital N's, that is the Avogadro's number, cancels out and we are left with nRT over 2. This is the case with a given gas. Now supposedly we have a monoatomic gas. Now for a monoatomic gas, we have n is equal to 3. Now with n is equal to 3, in that case we'll be having that value over there to be equal to 3RT over 2. So U is equal to 3RT over 2 in case of monoatomic. Now in case of diatomic gas, now we will be considering again the cases of temperature. So at low temperatures, where n is equal to 3, we have it to be equal to U to be equal to 3RT over 2. For medium temperature, we'll have n is equal to 5, and that gives U is equal to 5RT over 2. And then finally we have at higher temperatures, we have the value of n to be equal to 6 or 7. Again, as I say, 7 is usually taken for calculation purposes, so we take it as 7. So this is 7RT over 2. So these are the cases where we are getting the value of the internal energy of a given gas. And that's it from today's video. We'll be continuing with a few more things related to the topic in the upcoming videos. Till then, thank you for watching.